right, welcome everybody. So far in thermodynamics and kinetics, we've talked about things like rates of reactions, factors that affect the rate. We've also discussed other, other topics such as Hess's law. We've done potential energy diagrams. And so now what I wanted to talk to you about, which is kind of related to Hess's law, is using bond energy to figure out the heat of reaction. And we can do this by using a table of bond energy charts. But the format is a little bit different. And it's different because when we do bond energy, we do the energy to break the bonds. So the bond energy of the reactants, because the reactants, that's what we're breaking apart, minus the bond energy of the products. Because if you remember, we had this way of remembering bond energy, BARF. Break a bond, you absorb energy, release energy when you form a bond. So the reactants, we are breaking those bonds, and the products, we are forming those bonds. And so we do the bond energy of the reactants minus the bond energy of the products. And this is different from when we do Hess's law, where we do delta H of the products minus the delta H of the reactants. So always keep that in mind. So now when I look at this here, I have my C3H8. And one way to really do this and get this to work is to actually draw out the 3 carbons with all of the hydrogens connected. Just like this. We have 5 O2. So O2 has a double bonded to O, and there's going to be 5 of them. And I'm drawing these out for you. You don't have to necessarily draw these all out, but I'm showing you this. We have 3 CO2s on the products. 1, 2, and 3. And then we have 4 waters. So we have 4 of these waters. Okay, so 3 and then 4 waters. So what are the bonds broken? Well, the bonds broken are the bonds between the carbons. So we have 1, just undo that, highlight. We have 1, we have 2. So we have 2 carbon-carbon bonds. If we look in the chart at the carbon-carbon bond over here, we see that that is 347. So we're going to have 347 times 2. So that's the first thing. Then we're also going to break the CH bonds. And so let's count those up. We're going to have 1, 2, 3, 4, 5, 6, 7, 8. And we find the CH bonds, and we're going to break 8 of those. So we're going to have 413 times 8. So we're going to have plus 413 times 8. Then we're going to have the 5 O2 bonds. So the 5 O2 bonds are right here. They're 498. So we're going to have plus 5 times 498. That's all of our reactants. Now we're going to do our products. So minus our products. So we have CO bonds, 1, 2, 3, 4, 5, 6 of those. So if we look there, C double bond O is 805 times 6, plus we're going to have the H2O bonds. We have 2 in each times 4, that's 8 of them. And OH, when we look at that on this chart here, we have OH right here, and that's 464. It's 464 times 8. So now if we do this math, we'll see that we get a delta H for this reaction. Look at how strong that C double bonded O is. That's 805 kilojoules per mole. That's stronger than any of the other bonds that we see in the reactants or the products. The formation of those stronger bonds is really what's driving this reaction. The stability is increasing, we're releasing energy, the reaction is exothermic. And so because of that, this will release energy. This is a combustion reaction. Now something that we could do, if we wanted to compare the energy here to the energy that we would get if we were to just use the normal delta H's, CO2 got cut off, CO2's delta H is negative 393 kilojoules per mole. And so something that we can do is we can actually compare the two. And so that's what I'd like you to do. I'd like you to do this math down here to do the bond energy. And then I'd also like you to use Hess's law. And using Hess's law, figure out what the delta H is and see how close they come to each other. You're going to see that they're going to be really, really similar, hopefully. Okay, so that's bond energy. The other thing that I want to introduce to you in this video really quickly is entropy. Entropy, first of all, has this symbol S, or change in entropy is delta S. And the definition, as you'll see it often written, it is the disorder. So it's the disorder or randomness of a system. Some people will say chaos, how chaotic something is, how disorganized, how disorderly something is. The AP exam, they use the term dispersion, the ability to disperse particles. That's something new that they've introduced. But when I look at this, if I wanted to measure entropy, it actually has the units of energy. Its units are joules per mole times Kelvin. And when we do problems that are numerical, you'll see that we have to be careful with the units because entropy is in joules, whereas enthalpy or heat is in usually kilojoules. And those two tie together to tell you if a reaction actually occurs. But for now, we'll talk about when it increases and decreases. So when does entropy increase? Well, entropy will increase when the disorder increases. So you could have a really orderly phase of matter, something like solids. If I change that to a liquid, the particles have more freedom of movement, so they will be more disordered. If I add a solute to the liquid and make something aqueous, it generally is more disorganized. And if I take the aqueous and I make it into a gas or a liquid into a gas, it will become the most disordered. And when you think about a gas, the particles, they're not attached to each other. They're free to move wherever they want. They have total freedom of movement. This is a high state of entropy. Another time when it increases, or another case where it increases, is if you increase the temperature. So if you increase the temperature, the particles have more kinetic energy, they're moving faster, and they have more freedom of movement. The disorder would increase. And then also the last case is if you increase the number of particles. So in a chemical reaction, this really becomes important. If you start off with 2 moles of gas, and then you react those 2 moles, and they decompose, and you end up with 5 moles of gas, for example, the more moles of gas have more freedom of movement, more disorder, more randomness, the entropy will increase. When does it decrease? It's all the opposite of this. So gas going to aqueous, aqueous going to liquid, liquid going to solid. Decrease in temperature, and decrease in the number of particles. So what does this all have to do with chemical reactions? Why do we care about randomness? Well, randomness is sort of a way to measure stability. And in chemistry, we're all interested in stability. We already talked about stability in terms of bonds. We said that, when you release energy, that would be exothermic. That would give you a negative delta H. That would lead to an increase in stability. The less energy that something possesses, the more chemically stable it is. But then there's this other whole, part of stability that we had yet to talk about, and that is the entropy component. And with the entropy component, what we're looking at is positive change in entropy, positive delta S. When you increase the entropy or the disorder, this will lead to an increase in stability. And in nature, we see this happening. We see reactions that occur naturally and what they call spontaneously when they have these two characteristics. When they release energy, they're exothermic, and when their entropy increases, when their disorder increases. That's sort of like the best case scenario for increasing stability. And what we're going to work with is, what happens when you have a system that, doesn't have an increase in entropy? What is going to happen? Is the reaction going to actually occur? And it turns out that there's ways to really measure this, and ways and equations that we can use, and we can determine, will the reaction occur? Will it occur at all temperatures? And so we're going to do that during the next video. But for now, I just want to introduce this to you and give you the idea that entropy exists, the idea of disorder, and that in nature, things tend to move towards an increase in disorder, a decrease in energy. So thanks for watching.